of summer. We are calling it, as we do every year, the Summer of Soil. Make sure that you put that hashtag in all of your posts and all of those good things that you put up on social media. We will notice it, of course. My name, of course, is Brad Keeler. I'm the director of the Geo-Institute, and I am thrilled to welcome you in for the first of 3 summer cross-USA lecture presentations by Tim Stark from the University of Illinois. Of course, if you don't know anything about the Geo-Institute, after you watch this today, you should head over to geoinstitute.org. And there you will find out that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists. While you are there, if you are so inclined, and I hope you are, you can make a donation to our student participation fund to support Geo-Institute student programs. Donate $96 or more, and because we were founded in 1996, of course, you can get an amazing gift. We have some Carl Terzaghi bobbleheads remaining, not too many, and once they're gone, so you can choose one of those, or you can choose one of these killer pairs of GI socks, which Jay McKelvey calls dirt socks, and you'll get to hear from Jay in just a moment. I have one more thing to add. If you like what you see today, and I think you will, you should, of course, click like, subscribe, and get notifications. And if you do those things, we will let you know every time we post something to the YouTube channel. Now, the Cross USA Lecture is a joint venture of our Local Involvement Committee, Student Leadership Committee, and the GI Board of Governors. And so, from the Local Involvement Committee, to introduce Tim and to tell you a little bit more about the Cross USA Lecture, here is LIC Chair Jay McKelvey.
Thank you, Brad. Good afternoon, everyone. So as Brad indicated, the cross-country lecture is selected by the chairs of the Local Involvement Committee, the Student Leadership Council, and the past president of the Geo-Institute. The lecture is presented annually since 2010 to 5 chapters across the country and to 3 student chapters. This year's lecturer is Dr. Tim Stark, professor of an excellent faculty scholar of civil and environmental engineering at the University of Illinois, Urbana-Champaign. Tim's got over 40 years experience as a licensed professional engineer in 8 states. He's the past chair of the Embankments, Dams, and Slopes Technical Committee. Tim has over 375 publications, and today's lecture is going to be Highway Embankment Failures on Soft Clays. Without further ado, Dr. Tim Stark.
Thank you, Jay.
Thank you. I'm sorry, Tim, can we hold on just a second? We need to have a message from our sponsor, GeoPeer.
range here. We're going to focus over here on this soil ramp right over here. And there's about 115,000 cubic yard embankment. It's about 3,700 feet long. And right in this area where the little blue line is a creek went through here. And so you'll see a culvert in just a minute that was placed temporarily through the embankment during construction. And then this embankment, there was going to be a bridge across to the other embankment, which is an on-ramp to the interstate heading south. So prefabricated vertical drains were used to accelerate the consolidation of the soft clays under the embankment. That was known up front. They were weak, soft clays. And the drain spacing is 6 foot center to center. The drains are about 4 inches wide, 6 millimeters thick, and they were driven either 35 to 60 feet deep. A sand blanket, as you can see right here in the lower photograph, was installed on top of the ground surface to facilitate drainage of the consolidation water coming out of the foundation. T-shaped mandrel and anchor plates were used to drive the PVDs, and that's important because the hydraulic conductivity, the horizontal hydraulic conductivity or coefficient of consolidation is going to be important in just a minute. 320,000 lineal feet of PVD was installed. Some instrumentation was also installed. Here's a settlement plate to monitor settlement of the embankment, as well as some piezometers. So the embankment construction was going to be controlled, and the rate of filling could not exceed 1 foot per day or 5 feet per week because of the soft clay and allowing consolidation. Piezometers installed to monitor the pore water pressure, and if the change in pore water pressure exceeded 7 psi, and that's the change above the baseline water pressure, pore water pressure of 8 psi, so a total of 15 psi, the filling would stop. So the rate was controlled as well as the pore water pressure generation. Settlement monuments read weekly, expected 5 feet of settlement in some places. Here's the fill placement diagram on the top, the blue line. So fill starts on June 16th, 2007. It goes up, stops, and then it stops right here. This is an important date. This is July 13th, so about 1 month after fill started. The embankment is only about 8 feet high. The embankment was going to be 32 feet high. So that was 30 feet plus 2 feet of surcharge on the top. But at 8 feet, tension cracks started developing. The fill was stopped, and that's why you see the fill diagram horizontal here for about a month or so. And then fill continued, and I'll explain that in just a minute. The lower graph is the pore water pressure. And from piezometers, so notice the pore water pressures are increasing. And right here, they spike up, and that's the onset of the tension cracks when the embankment is 8 feet high. So fill stopped, as I mentioned, for about a month, and you can see the pore pressures decrease a little bit, and then fill is restarted. And a few days later, July 25th, the total pore water pressure reaches 15 psi, and so that exceeds the baseline plus 7. So again, filling stopped for a little bit, filling restarts again, pore water pressure goes back up, and finally it exceeds 15 and work is stopped on August 1st. So about a month after, about a month and a half after fill placement started. The dashed black line is the change in pore water pressure of 7. Okay, so the change in pore water pressure is approximately 8 to 14 psi. So here's the initial 8, and 14 is, say, right about here. And then, of course, it goes up to about 16, 16.5. But if you just use that change in pore water pressure, let's say 75% of the total stress that was applied, you would estimate, just round numbers, about a 25% consolidation. That's going to be very important because the design was assuming significant consolidation of the soft clays and thus a significant increase in undrained shear strength, allowing the embankment to be constructed to 30 to 32 feet. So you can see that the degree of consolidation here, even early on, is fairly low, only 25%. And I bring that up because this is a really important way to track how the soft foundation is consolidating. So if you have some piezometer data, you can sort of track how it's progressing, and then you can change or slow the fill rate if needed. Okay, so let's move forward to July 13th, 2007. This is the first onset of tension cracks that I mentioned. And after these tension cracks showed up, work was stopped and a geotechnical study was started to investigate the cause of the cracks. So the fill is 8 feet of the 30 that was needed. And of course, they were going to go to 32. The 2 foot would be a surcharge. So they would take that off and then put the pavement system on. And again, that corresponds to about a 25% consolidation. Here's the tension cracks, just to give you an idea what they look like. Here's some going across the top of the embankment there. On July 24th, about 11 days later, filling continues with added monitoring. So some survey points and so on to more carefully monitor the embankment. Here's some more tension cracks that developed on July 13th. Okay, so ODOT performs the geotechnical evaluation and let the filling continue about 11 days later with some survey pins, etc., installed. That goes until July 30th. More tension cracks develop after the fill reaches now 13 feet. So it's not even half the height of the embankment. August 1st, about 1 month after start, the pore water pressure is greater than 7 psi, the change in pore water pressure, so work is stopped. Survey pins show uplift and toe rotation outside of the embankment area, basically off the property. And I'll show you a photograph of that in just a minute. August 2nd, cracking from station 202 to 207, about 500 feet long, develops. August 6th, a 1.5 foot high scarp at the ramp center line develops, and it displaces a chain link fence that separates the right of way from a private property. And I'll show you a photograph of that. And that confirms the survey pin showing uplift and toe rotation. Okay, so here's August 2nd. Here's the scarp running across the embankment there. And here's a close-up of it on the right. The embankment's unsaturated at this point. There's August 6th, 4 days later. So here's the scarp developing, and it continues to develop. Here's August 22nd. Oops, and here's more development. And here's on the 22nd, you can see this fairly deep scarp right here. October 15th, there's the scarp. There is some rubble concrete rubble fill behind it, and which was kind of interesting. The scarp formed in front of the concrete rubble, but that was allowed. The contract allowed for 10% of the fill to be concrete rubble, so that's why it's there. And now here's the chain link fence that I mentioned earlier in the private property on the left. This fence used to be a straight line right across there, and here's a close-up of it. So the toe rotated up and rotated out, pushing the fence onto the other property. I mentioned a culvert installed for the creek. There it is. It was a temporary culvert, and so after the movement of the fence and the stoppage of work, the embankment was excavated to figure out what was happening. And that's a picture of the culvert after it was exposed. You can see it was basically sheared and indicating movement in the foundation, sort of shearing off the culvert and moving it towards the fence, the chain link fence. Okay, So everybody, that's the good news. Yeah, I know. That's the good news. Bad news is the remediation. A number of techniques were proposed to remediate this embankment area. And what was driving the remediation is a potential contract delay of about $250,000 per month. Some of the possible remedial measures included lightweight fill, deep soil / concrete columns, geogrid reinforced granular embankment, and other geotechnical type remedial measures. However, and this is the bad news, it was decided to replace the embankment with a pile supported bridge. And that's what you see in the photograph. There's the bridge. So all that embankment material was removed and piles were driven for each of the bridge bents right here. And that off ramp, even today, is a bridge. And there it is, an aerial photograph. There's the bridge ramp to I-71 heading south. So that's unfortunate that it turned out to be a structural remedial measure instead of a geotechnical remedial measure. But the delay costs built into the contract and so on, some uncertainties about the geotechnical conditions and the performance of the geotechnical remedial measure led to a bridge. So that's really the bad news of the case, that we couldn't keep it as a geotechnical remedial measure. Okay, so let me focus on the three causes of the failure. First, stratigraphy, the horizontal coefficient of consolidation, and finally, the embankment strength. These three factors, I think, really contributed to the failure occurring. Okay, so let's talk about subsurface conditions first. This is the design cross-section used in the initial designing embankment. Notice that the soft clay layer is about 12 feet thick right here, and it has an undrained shear strength of about 250 pounds per square foot. And the embankment is on top right here, and it's giving a shear strength parameter of C equals 1,500 pounds per square foot and phi equals 0. So this is the design cross-section boring 8A, which is in the slide area or the failure area, but there's another boring that is also in the slide area. This one's at station 201 plus 61. The next boring is 8C, as in Charlie, is at station 203 plus 58. Notice now that the soft clay layer is deeper. There's 250, 250, just as you saw in the prior cross-section. But now at a deeper depth, there's an even weaker clay layer, and that's about 10 feet thick from 954 to 964. And a slope inclinometer was installed. That's what this purple square is right here. And that was projected to this station 203 plus 58. And it puts the failure surface in this weaker clay at a deeper depth. And this corresponds to the old stream area. So there's a thicker weak layer here. It goes from 974 to 954, about 20 feet thick, and the bottom of it being even weaker than 250 pounds per square foot undrained shear strength. So the lesson on this first takeaway, or the first cause, is must find the critical cross section. Plot up the borings, find the thickest and weakest clay layer, and that's where the design should focus on. And this cross section's in pretty good agreement with the fence being pushed out on the left up here and the scarp developing here in the cohesive fill. The inclinometer was at station 200 plus 00, so it's projected about 350 feet. Okay, that brings me to cause number 2, the horizontal coefficient of consolidation. That is important because, remember, the prefabricated vertical drains were installed, so we're interested in the horizontal coefficient of consolidation, not the vertical coefficient of consolidation. Okay, because drainage is going to occur radially or horizontally, not vertically. Okay, so the idea of the PVDs was to speed up the consolidation of the soft clays. And so here are the design values of the undrained shear strength in the foundation, as I showed in the last cross section at 203 plus 58, 250, 250, and the weakest layer being a undrained strength of 200. So at the end of construction, there would be no consolidation, 750, 250, 200. But the design at the end of primary consolidation at 15 feet of fill assumed that there would be 824, 732, and 477 undrained shear strength in those 3 weak layers, because the prefabricated vertical drains would accelerate the consolidation and allow end of primary consolidation to occur when the embankment reached 15 feet. That would yield a factor of safety, an undrained factor of safety of 1.8, which would indicate stability. Now, if you remember, the tension crack started developing at 8 feet and the embankment failed at 13, so it really never made it to 15 feet. Okay, but let's keep going with the design. So then after 15 feet, they would increase the embankment to 30 feet, which is the final height. So initially, right after construction to 30 feet, the undrained strengths would still be 824, 732, and 477 because no consolidation. And then the factor of safety would be basically one, or at failure. So they knew it was close. But at the end of primary consolidation at 30 feet, now the undrained shear strengths would be 1398, 1213, and 757, which would yield a factor of safety of almost 1.5. And that would indicate the embankment would be stable at 30 feet. Again, it fails it starts cracking at 8 feet. Okay, so here's the fill placement diagram that I showed you earlier. And again, a quick calculation on the increase in pore water pressure compared to the increase in fill height, or delta sigma, would give you an indication that it was really only a 25% consolidation, not 100% or end of primary. So why did that consolidation not occur? And for all the design engineers out there, my hat's off to you. It's far easier to look at a case after the fact when you know the answer. The hard part is to look at the soft clay up front and get it right. So my hat's off to all the design engineers that are listening. You really have the hard job. My job is kind of the easy job because I know the answer. I know when the factor of safety reached 1. And so it's a much easier analysis. So with that in mind, that's the first bullet, easier than design. The design analysis had a C sub V of about 19 to 26 or 27 feet square per year. However, the design assumed a horizontal coefficient of consolidation of about 200 feet squared per year. And you can see that here on the right from the geotech report. It comes down and says the design of the wick drain system, it is recommended that C sub H be utilized for design of 200 feet squared per year. Well, that would yield a design ratio of C sub H to C sub V of about 7.5 to 10.4. And so one of the takeaways here will be, what is a reasonable CH over CV to use for design? And there's a blow up of the recommendation of CH being 200 feet squared per year. You'll see on a slide in just a minute, this ratio of 7.5 to 10 is too high. And so the design inherently assumed there would be more radial or horizontal drainage and thus consolidation than actually occurred. So that brings me to the ASCE method. And this is really a great method for using field settlement data to estimate the mobilized or field C sub H data when prefabricated vertical drains are installed. So this is a paper by ASCE in 1978, and you plot the settlement data on a graph of settlement at one plate versus settlement at another plate. And so that's what you're looking at going here. And you draw a line through that. And here's the end of primary right here. And so you can use this plot, and there's some equations. I didn't include all the equations, but they're all built into Asaoka's paper. They're also in my technical paper. And that yields a mobilized C sub H of about 68 to 91 feet squared per year. So if you are remembering, the design is 200. So this is about a quarter to about half of the design C sub H. And that's really why the foundation clays were not consolidating as fast as it was assumed in the design. The low horizontal coefficient of consolidation could be due to smearing, clogging, or a lack of drain capacity to dissipate the consolidation water to the sand blanket at the top or permeable layer below. So either way, the C sub H ends up to be about a quarter to a half of the design value. And here's the design analysis. So the C sub H is 7.5 to about 10, the ratio. So a typical design ratio is only about 1.5 to 4. So if you don't have the value of C sub H, use your vertical coefficient of consolidation and multiply it by 1.5 to 4. Maybe a good number might be 2. And if you would do that, 2 times 68 would only be like 136, not 200. And so using the Asaoka value of C sub H, you calculate a ratio of 2.6 to 3.6. Okay, that ratio is nicely within the typical ratio of 1.5 to 4. And this is the main reason why the foundation clays did not consolidate as fast as was assumed. Okay, so takeaway lesson number 2. Use a ratio of C sub H to C sub V of 1.5 to 4. The first takeaway is find the critical cross section, find the weakest soil stratigraphy, and use that for design. Okay, so the Asaoka method, verify design assumptions and C sub H, and this follows the observational method with Professor Peck. Design for the most probable conditions, understand problems for most unfavorable conditions, such as the C sub H being a quarter to a half of the design. Select quantities to be measured and calculated during construction. And so this case would be settlements of the embankment, and then your calculation of C sub H using the Asaoka method. And once you've calculated C sub H using the Asaoka method, you could see that it was not consolidating as fast, so you could change the fill rate procedure such that you did not have the failure. Select design modifications if deviation, start construction and measurements, and adjust filling rate to maintain stability. This turned out to be a pretty expensive repair with the bridge replacing the embankment, and so having this in place could have saved a substantial amount of money. Okay, so here's the inverse analysis. Again, it's easier when you know the answer to all the design engineers listening. If I use the Asaoka C sub H of 68 feet squared per year, that gives me the blue line right here. The design C sub H is 200, which is the red line. So notice after about a month and a half, the design C sub H predicts about a degree of consolidation of about 90%. Whereas the mobilized C sub H predicts a degree of consolidation of only about 55%. And remember, the pore water pressures that I showed you earlier indicated only about 25%. So you can see that the foundation was not consolidating as quickly as was assumed, and thus work stopped on August 1st. And here's the piezometer response. As I mentioned before, the piezometers This is the critical cross-section right here, boring 8C. The design cross-section, this is the boring 8A I mentioned earlier, is over here on to the left, and the failure developing right here around boring 8C. Okay, yep. And there's the piezometer right there, right close to boring 8C, and that's what gave the piezometric response I showed earlier and above. Use settlement plates, and that's really important because that allows you to use the ASCE method to estimate your mobilized C sub H. Okay, that brings me to the third cause, embankment strength. Third takeaway. So the inverse stability analysis is also a lot easier than the forward analysis. You don't know the answer in the forward analysis. In the inverse analysis, you know the answer. It's the factor of safety is 1. So it's much easier. So my hat's off to all the design engineers. The stations 202 to 205, that's where the old stream is. And so that's where we focused the cross section. And here's the same cross section, 203 plus 58. Here's that weak clay layer at 200 pounds per square foot and the inclinometer in it. So the embankment strength in this cross section is a cohesion or an undrained shear strength of 1,500 pounds per square foot and phi equals 0. Remember earlier on, I mentioned the embankment is unsaturated. So if it's unsaturated, we really can't assign it an undrained shear strength. And that's really going to be the takeaway of this third piece. So the design factor of safety had an undrained, the design undrained factor of safety was 1.6 at a height of 15 feet. And that's why it was assumed to be okay for design. But the embankments failed at only 13 feet. So again, we know the answer is 1.0 at 13 feet. And that's well less than the 32 feet that was the focus. But you can quickly do a bearing capacity analysis before you do your slope stability analysis, and you could see that this was going to be a problem if the consolidation did not occur. So that's what's next. Here is the undrained bearing capacity analysis. So we can verify the design factor of safety of 1.6 at 15 feet using a quick bearing capacity analysis and see if it works. And here's the bearing capacity equation, N sub C times the average undrained shear strength across the failure surface. I'll show you that in a minute. The gamma of the fill embankment and the height of the fill. So this is actually a homework problem in Peck, Hansen, and Thornburn's book, Foundation Engineering. It's chapter 18, number 10. And I use it a lot. What is the approximate factor of safety against failure for a 30-foot high fill? Exactly our case. Weighing 125 pounds per cubic foot, it rests on a clay with an unconfined compressive strength of 1.5 TSF. And the answer in the book is 2.0. The question is over here on the right, page 303 in Peck, Hansen, and Thornburn. So here's the analysis to solve that homework problem. There's the bearing capacity equation at the top with phi equals 0, n gamma is 0, n q is 1, and n sub c becomes 2 plus pi or 5.14. So I plug in those numbers, and that gives me 5.14 times SU over gamma h, which you saw here earlier. Now I plug in the numbers. Unconfined compression, take a half of that, and divide it by a 30-foot high fill, you get a factor of safety of 1.98. So you would get that homework problem right in Peck, Hansen, and Thornburn. So now let's apply it to station 203 plus 58. So we have to come up with an average undrained strength across the foundation. And that's what's in this equation here. So 750 times 8 feet, 250 times 10 feet. And that's those two layers of 250 pounds per square foot. And then about 60 feet from about here to over to here for the soft clay at 200 pounds per square foot. And then I divide by 8, 10, and 60. That gives me an average undrained strength along the failure surface in the foundation, only the foundation. I'm going to get to the embankment in just a minute, of 230.8. So I plugged 230.8 for undrained shear strength, average, 130 unit weight, and the embankment's 15 feet is the design. Notice my bearing capacity factor of safety is 0.6. Nowhere near 1.6. Okay, so even before the slope stability program is turned on, perform this quick bearing capacity analysis and know where you are in the process. So when the computer does go on and the brains go off, you kind of have some guardrails on the analysis. But here, just a quick bearing capacity analysis shows that the embankment would not be stable at 15 feet. And as you saw, at 8 feet, it started cracking. So let's try 8 feet now. So if I use my average undrained strength of 230.8 and I divide by 8 feet of embankment and 130 unit weight, I get about 1.1, which is a little higher than 1.0, but clearly this shows that the factor of safety is not 1.6. Even getting to 8 feet is going to be close to failure, and certainly getting to 15 or 30 feet is going to lead to failure. So again, just try a quick undrained bearing capacity analysis before you engage with the full slope stability analysis. Okay, so here's a table that summarizes those factors of safety from the undrained bearing capacity analysis. At 8 feet, there's 1.14 that I just showed you. Tension cracks restart at about 13 feet. The factor of safety is 0.7. 15 feet, 0.6, and 30 feet, of course, would be even lower. So the critical height for the embankment, you can calculate using the bearing capacity analysis, is about 9.1 feet. Pretty good agreement with the tension cracks starting at 8 feet. Okay, so that's a quick use of the bearing capacity analysis. But that still doesn't answer the question why failure occurred at 13 feet and why the undrained factor of safety of 1.6 at 15 feet is incorrect. And that gets to the shear strength of the embankment fill material. So the compacted fill strength parameters are C of 1500 and a phi equal to 0. So notice this is the moment equilibrium factor of safety equation. So phi equals 0, this term drops out, and you're left with C times the length of the failure surface through the embankment. So at 15 feet, you would be multiplying 1,500 pounds per square foot times 15 feet. And that basically inflates the factor of safety because you're generating so much strength out of the embankment compared to the soft foundation. And that's the real takeaway on the third piece is the compacted fill strength can't be 1,500 pounds per square foot. So that came from what is now an inactive Geotechnical Bulletin number 6. This bulletin is no longer active, so do not use it. But if you come into the bulletin at a soil type of A7-6, which is the clay, you get 1,500 pounds per square foot. And that's where C is 1,500 and phi is equal to 0. There's a drained friction angle below that is a function of PI, and the PI is 10, so you would estimate a friction angle of 33 degrees, effective stress friction angle, and a C prime of 0. So that would be a better parameter to use than the undrained shear strength for an unsaturated embankment, okay? But that's still a problem because the cohesion of 1,500 is multiplied by the full length of the embankment. So what you need is a tension crack. So you can calculate the depth of tension crack using this equilibrium equation, 2 times the cohesion of the fill divided by gamma fill 45 minus phi prime over 2. So if you calculate that, the tension crack is 23 feet for C of 1500, which was assumed in design. So unfortunately, we're online, but I hope everybody online realizes the importance of 23 feet here. So that means the embankment would have no strength for 23 feet. So at 8 feet, it should have no strength. At 13 feet, it should have no strength. So it failed at 13 feet because it had C of 1500, whereas really there should have been a tension crack that prevented the embankment from generating any strength in the stability analysis, thus making the stability analysis essentially the undrained bearing capacity analysis I showed you. So last bullet, no embankment strength. So don't forget, most slope stability software allows a tension crack, and you can put the tension crack in with water or without water. We used without water because it was fairly dry. You saw how dry the embankment is, but if you add water, that would put a lateral stress also on the tension crack. Shear, and Duncan have a more sophisticated equation that takes into the count the modulus difference between the fill and the foundation to calculate the depth of the tension crack. And that's shown in this equation. K is the modulus of the foundation. K of the fill is the modulus of the embankment fill. C is the foundation, and the width and depth. So using Shear, and Duncan's procedure, you estimate a tension crack of 15.5 feet. So again, the embankment would contribute no strength because of the strain incompatibility between the soft clay in the foundation and the stiff embankment on top. Okay, one last point on the stability analysis is determining the undrained shear strength. For design, the undrained shear strengths that I showed in the cross section were estimated from SPT blow counts. And the correlation by Bowles of SU is 6 times N was used. The correlations for undrained shear strength with blow count tend not to be reliable, and that's stated by Peck, Hansen, and Thornburn, 1974. Standard penetration correlations for clays can be regarded as no more than a crude approximation, but for sands is often reliable enough to permit the use of N values in foundation design, which Peck, Hansen, and Thornburn is built on for sands. So instead, use the plasticity index and estimate your undrained strength ratio by a correlation such as this. This is from Terzaghi, Peck, and Mesri. You could come in at, say, direct simple shear or triaxial compression, and you would estimate an undrained strength ratio from, say, 0.22 to about 0.32. If you want a mobilized unstrained strength ratio, 0.22 would be a good value. So you could use that for your undrained strength estimate. So, and then if you looked at the long-term stability of the embankment, you use effective stresses, as I mentioned earlier, phi prime in this bulletin, or you could use our spreadsheet, which gives you fully softened strength, and that would be the long-term strength of the compacted embankment. It could soften over time, over the service life. So design the embankment using the drained, fully softened strength, which is shown here. There's the friction angle, fully softened friction angles from 32 to 21.6. And here's the fully softened envelope, 0 to about 158. Fully softened is the black line here, and the residual friction angle is the red line. Okay. So summary of the stability analyses. Draw a new cross section where there are changes in soil stratigraphy, and use those to locate the critical cross section for stability analysis. So review the borings carefully, find the weakest layers. Big impact of the cohesion or undrained shear strength on factor of safety. So for the embankment, you can't assign it a C value or undrained strength value without a tension crack because of strain incompatibility. So if you use an undrained strength for the embankment, you must use the tension crack, and you can estimate that by equilibrium or Shear, Ponto, and Duncan's analysis. Finally, before the computer analysis for factor of safety is undertaken, perform a quick undrained bearing capacity analysis. Understand what the guardrails are for your factor of safety and the critical height of the embankment before the software starts up, so you kind of have an idea of what the answer is going to be. Shear strength correlations. Use those for planning level design. Use Atterberg limits, not SPT, to estimate the undrained shear strength if you're going to use that for the embankment. Also, you can use the Atterberg limits to estimate the fully softened strength for the compacted embankment. And for the foundation, instead of blow counts, you could, of course, use the cone penetration test. Okay, so to wrap up, 3 reasons for the failure: stratigraphy, the value of coefficient of horizontal coefficient of consolidation, and the fill strength used for the embankment. So when you have a stiff embankment over a soft foundation and you're using an undrained strength or a C for the embankment, include a tension crack. You can estimate that using this simple equilibrium equation. Don't use a blow count to estimate SU. Use PI and get an undrained strength ratio. Use your undrained bearing capacity to guide your short-term or end of construction analysis. Use a reasonable range of C sub H over C sub V of 1.5 to 4.0. So if you only measure C sub V in typical consolidation or odometer tests, multiply that C sub V by a value in between 1.5 and 4, say maybe 2, and then use the ASCE-OCA method during fill placement to estimate the mobilized C sub H and make sure that the consolidation is occurring as you predicted it or assumed. If not, modify the fill, reduce the filling rate such that the consolidation occurs and you don't end up with an expensive failure. Okay, the next national lecture is on July 18th, and I will discuss a cement, bentonite, and jet grouting cutoff wall performance. So thank you so much for joining, and I look forward to your questions.
Well, thank you very much, Tim. Excellent presentation. I'm going to start the questions off. Why is a tension crack needed, and should it be filled with water?
Okay, great. So yes, the tension crack is needed because there's a strain incompatibility between the soft foundation and the stiff embankment. So in other words, you will get to peak or failure in the foundation quicker than you will in the embankment. And so second, the embankment strength of that C is getting multiplied by the 30 feet or full height of the embankment if you do not have the tension crack. And that dominates the factor of safety equation. So you need the tension crack because generally you're not going to develop that strength in the embankment before the foundation clays fail. And the second part you asked about is the water. So you can put water in it if you want. That just puts a little more pressure on the slide mass. But in this particular case, we didn't. It was fairly dry.
Okay, great. Where can we get a copy of that spreadsheet of yours, the shear strength?
I'd be happy to send it to anybody. Please just send me an email message. I'll send you the spreadsheet. It's based on liquid limit or Atterberg limits, and it gives you the fully softened strength and the drained residual strength. Yep, happy to send it to anybody.
Awesome. Okay, let's hear from the audience, see if we have any further questions.
Let's see, can I put it in the chat? I can't. No. No, I don't think I can upload the spreadsheet in the chat. Okay, go ahead, Jay.
Okay, Tom Richards is asking on slide 31 on your strength gain predictions, why does the top 8 feet gain so much strength at EOP?
Okay, so the top layer gains strength. Thanks for the question, Tom. because remember there a sand blanket was installed. Let's see, it was about 1 to 2 feet thick. And so there's an active drain close by the top layer. So it's able to drain quicker than the deeper layers.
Very nice. Could you provide the name of that paper again that you're referencing?
Yes, and I'm happy to send it to anybody. Case study, vertical drain and stability analyses for a compacted embankment on soft soils. It is in the Journal of Geotechnical and Geo-Environmental Engineering. It is on, let me see, dated. Oh, it's in 2018 February issue. 2018 February issue. And I'm happy to send it to whoever wants it.
Awesome. Nick Trimble asks, he's curious about the shape of the shear failure. On the soil profile section, the red dashed failure line was circular, but daylighted before the fence. So why did the fence displace?
Well, actually, on the failure section at station 203 plus 58, I extended the cross section out to the fence, so the fence was actually shown on the cross section. So I did extend the failure surface out to the fence on the failure section at station 203 plus 58.
Okay. Would you take the same approach for organic clays or peat, even fibrous, as you would for these soft clays?
Yes, you could take the same approach. And there's actually a couple papers on peat shear strength by my colleague, Professor Riza Mesri, in the Journal of Geotechnical Engineering. And there's also one on the compressibility of organic or peat soils. So you could use the same approach. You're just going to use a different SU value for the clay. Instead of what I showed, you'd use it an SU for a peat.
Okay, this is a great question. What geotechnical remediation would you have used instead of the piled bridge?
Man, that is a good question. I think we could have done some either lightweight fill or done some ground improvement in that area that could have gotten the embankment to its design height. Unfortunately, that didn't come to pass. There were design issues and it ended up being a bridge.
Good. If the designer had not overestimated the C sub H values and the embankment had been built slower, would the anticipated gains in shear strength been reasonable?
Yeah, I think so. It's just if they would have viewed a C sub H around, let's say 70, that would have slowed the construction down, obviously, but that would have given them the strength gain they were looking for. Yeah, okay. I think it could have been done.
Okay. This question is, maybe I'm missing something, but there didn't seem to be any reduction in strengths due to pore pressure buildup in the subgrade soils. But even if you use the end of construction numbers, they predicted a factor of safety less than 1. Can you comment on that?
Yeah. So the undrained shear strength value incorporates the pore water pressures in the analysis because it's going to be a total stress stability analysis. So the unconsolidated numbers or the initial design numbers of 250 and 200. So that's the end of construction, and that means there's been no dissipation or no consolidation of the foundation soils. But if the C sub H was correct and it was allowed to consolidate, it would go from 250 up. And that was really what the problem was.
Okay. Why didn't you include an undrained shear strength of 1,000 PSF of the bottom layer in calculating the average undrained shear strength?
Oh, because the bottom layer was outside the failure surface. So the failure surface goes down to the gray silty clay, and that's the bottom layer. Great question and good observation of the cross section, which has an undrained strength of 1,000. So that's like a firm layer below the soft clay. So when we have that situation, the failure circle or composite surface will go down to that stiff layer and come back up. And so a composite surface, actually somebody could ask, could that surface have been a composite surface? And it could have been, where it would be a circle down to the top of the stiff silt, along the stiff silt, and then a circle back up to the fence where it pushed the fence off. But good question, good observation. It's that layer was just a lot stronger, 5 times stronger than the layer above it.
Could you comment on the effect of a high strength or high modulus geosynthetic geotextile geogrid placed at the ground surface? What would that have had on the stability of the embankment?
So that was one of the remedial measures suggested, that as well as a reinforced platform. So the issue there is you would need some displacements to mobilize that tensile resistance of the geogrid. We weren't sure how much it would take. In addition, remember the failure surface has already occurred. So we're no longer operating at peak strength. We're operating at a residual strength. And so we looked at a geogrid and a geogrid reinforced platform and just didn't think it could support the embankment to 32 feet because we already had a failure surface in the subsurface.
Okay. Why would you take H horizontal for bearing capacity for a soft clay layer? I'm not sure if I understand the question.
Take H, what was it?
H horizontal for bearing capacity for soft clay layer. Not sure if I understand the question.
Well, no, I'm taking H of the fill for the bearing capacity equation. So the fill is like the footing on the ground surface. So instead of a footing, it's a fill of a height 30 feet or 15 feet. And that's what's used in the bearing capacity equation.
Okay. Should the formation of the tension crack initially not be a cause for caution, reevaluation of the embankment stability?
No, I disagree. The tension crack is telling you what's happening. And so right there early on, July 13th, when the embankment's at 8 feet, when those tension cracks, and they ran along the embankment, that showed the onset of movement. So I think it was really prudent to do the investigation. Unfortunately, fill was continued and eventually it failed. But you know, the tension cracks are an important thing. Always determine whether it's a tension crack or a settlement crack. If it's a tension crack, there has been shear movement.
Tim, what was the undrained strength ratio they used in that lower clay layer in the design?
Well, they didn't use it in design. We used 0.22 in our forensic or inverse analysis, an undrained strength ratio of 0.22, because the lower layer was basically like a direct simple shear test.
Was there any indication of how C sub H was determined in the geotechnical report? Was it just an incorrect assumption, or was there any validation to that?
No, it was assumed value, and I showed the report. The statement says, however, it is recommended that the following C sub H be utilized for design. That was it, just an assumed value of 200. And there are consolidation tests, vertical consolidation tests. So they could have checked that ratio and seen that it was about 7.5 to 10, which is really outside. the normal range of 1.5 to 4.
Okay. Last question. Should fully softened strength be used for embankment or firm to stiff clays?
Yes, for the long-term condition, right? So we have short-term, which is end of construction. That's where the tension crack has to be applied. So you don't use a undrained shear strength for the embankment in the undrained or total stress analysis. But then the second analysis is the long-term analysis, and that's the drained analysis, where you assume the clay foundation has consolidated to 100%. So now you can use a feed prime for the clay as well as the embankment. And that would be a fully softened strength because the embankment's open to wetting and drying cycles through rain and etc. So use fully softened strength, drain fully softened strength for the long-term analysis of the embankment.
You would not use a peak strength.
Correct. Correct. Because if you use the compacted peak strength, it's going to soften over time, and you will, again, overestimate the embankment.
Okay. All right. Well, thank you for these great questions, Tim. Thank you for an awesome presentation. I'm going to kick it back to Brad, who has some summary comments for us.
Great job, Jay, moderating, and great job, Tim. That was a fascinating lecture. The Cross USA is always pretty special, and it gets a little bit of a different audience than many of our award lectures get. So it's always cool to hear. I want to thank everybody for their questions today. It's awesome to see everybody participating out there. Now, a little bit of behind the scenes here. We always tell the moderator, have a few questions ready just in case nobody asks anything. It was not a problem today. Thank you for going rapid fire with everybody. The participation was great today, and we do really appreciate that. And it's your opportunity to really get a lot more out of the talk than you would have otherwise. We do apologize for the audio issues right there at the beginning. It was just a few seconds in the end, but every delay we know on the internet seems like hours long. So thanks for being patient with us and sticking with us today. Again, if you liked what you saw and you're still watching, so you probably did, click like, subscribe, get notifications, and we'll let you know every time we post something to the YouTube channel. Tim mentioned the next Cross USA live stream coming up on July 18th. The link is over in the chat box to the right of where you're watching this. You can register for that right now on our Eventbrite. While you're there, you might want to think about registering for our next couple live streams as well. Next Tuesday will be GeoStrata Extra. Editor Chris Woods will be interviewing Billy Camp and Scott DiFiore on the need for a ground improvement standard. So you're going to want to check that one out. Next Thursday, June 15th, is part 4 of our Keller Seismic series with Jeff Bachhuber from PG&E, and he'll be talking about the Diablo Canyon nuclear power plant. So you do not want to miss that as well. We'd love to see you at both. As I always say, we will see you in the chat. Thanks again, everybody, for sticking around today. Thanks, Tim. Thanks, Jay. What a great afternoon. And we will see everybody very soon.